In this video, I'm going to talk about the chemistry of hydrogen, both as an atom and as a molecule. So if you've looked at a lot of different periodic tables, one of the things that you may have noticed is that not everybody puts hydrogen in the same spot on the periodic table, because where you want to put it depends to some degree on which of its properties you want to talk about. If you want to talk about the fact that the electron configuration for a neutral hydrogen atom is 1s1, and therefore we can oftentimes remove one electron and make a hydrogen plus one cation, then you're going to tend to put hydrogen at the top of group 1, because lithium and sodium and potassium also have electron configurations that end something s1, and they also make plus one cations. But if, on the other hand, you want to talk about the fact that hydrogen only needs to gain one more electron in order to attain a noble gas electron configuration. If we give it one more electron, it has the same electron configuration as helium. And if we want to talk about the fact that hydrogen as a molecule is a diatomic species with a single bond, then in that case, it actually makes a bit more sense to put it at the top of group 17. Because in those respects, it's quite similar to the halogens. It's a gas, it's diatomic, and if we add one electron, we make an anion that has the same electron configuration as a noble gas. But then sometimes we're more interested in the electronegativity of hydrogen. Is it going to be the positive end of a bond, or is it going to be the negative end of a bond? And if you want to use periodic trends in order to predict your electronegativity, you actually want to sit hydrogen on top of boron. That's the right spot in order to predict its periodic trends relative to the other elements on the periodic table. So if we care about its electronegativity, we're going to put it there. Not a lot of people do, but that's where it belongs if you're talking about electronegativity. And for this reason, you're also going to see many periodic tables just give up completely on finding a good home for hydrogen. And what they do instead is right in the middle, floating at the top, they say, this is our representative element, and we're going to tell you where everything for an element is. And oh, look, we picked hydrogen as our representative element. There's its atomic number. There's its mass. And if I could fit it on top of there, I might write in its name as well. So this makes hydrogen pretty unique. There is no other element in the periodic table that can be argued to have more than one viable location on the periodic table. So as we noted on the previous page, the electron configuration for a neutral hydrogen atom is 1s1. And that means then that if you wanted to make a hydrogen cation, you would take one electron away. And for lack of any better way to write it, I guess it would have an electron configuration of 1s0. It has no electrons at all. And we could say, therefore, that, well, it doesn't really have a noble gas electron configuration because there's no noble gas that has no electrons and no protons and just doesn't exist. We can say that all of the shells of electrons here are either completely filled or completely empty. We have our neutral hydrogen atom, which, as noted above, has an electron configuration of 1s1. And therefore, since it only has the one valence electrons, we wind up getting a stable molecule with a single bond between two hydrogen atoms. So to achieve a noble gas electron configuration that actually matches a noble gas that exists, we actually need our hydrogen atom to gain an electron, which means we need to make the hydride anion, which has two valence electrons. And this has the same electron configuration as helium. And this is, in fact, an ion that forms. Sodium hydride exists, potassium hydride exists, calcium hydride exists. Hydrogen can, in fact, make anions in addition to being able to make cations. Another thing that's really important to be aware of about hydrogen is that the hydrogen-hydrogen bond is very strong. And the simple reason for this is that hydrogen atoms are tiny. And so that hydrogen-hydrogen bond is a very short bond compared to the vast majority of other single bonds. And so even though there are only 2 electrons holding those 2 hydrogen nuclei in close proximity, because the 2 hydrogen atoms are so small, the electrons in the bond are able to be simultaneously very close to both nuclei at the same time. And that creates a situation that's extremely favorable and that therefore requires a lot of energy input in order to break open. And so what that means is that hydrogen actually isn't that reactive of a gas. It's easy to make, as we'll see on the next slide, but there aren't a lot of things that it will react with without help. People tend to think of hydrogen as being very explosive because of things like the Hindenburg explosion, where we had this giant hydrogen-filled balloon. But if there hadn't been fire around to promote the reaction of the hydrogen gas with the oxygen gas to overcome the huge activation energy for that reaction, that explosion would never have happened. Hydrogen gas and oxygen gas mixed together at room temperature with no spark or energy source are fine. Just don't light a match. If you light a match, then you're going to start triggering a very exothermic reaction. And once that exothermic reaction starts going, it'll snowball from there. And so once we have enough energy to start the reaction between hydrogen and oxygen to make water, then we get a reaction that looks like this. But it does require some sort of spark or fire or significant external energy input to get that reaction going. You'll see later on in the course, hydrogen also reacts with nitrogen gas to make ammonia. But in order to get that reaction to go, we have to operate at high temperature, high pressure, and with a catalyst. The reaction doesn't just go on its own. Practically the only thing that hydrogen gas will react with on its own is fluorine gas. And when hydrogen gas and fluorine gas react, we get HF, hydrogen fluoride, or if you prefer, hydrofluoric acid. And so we can see that getting hydrogen to react is actually quite tricky because we have to break that very strong, very high energy bond. On the other hand, making hydrogen is quite easy. And you've seen how to make hydrogen in the lab in several different ways already this semester. You've seen that if you take a metal and react it with an acid, that you make hydrogen gas. For example, you take zinc metal and react it with aqueous acid of some sort, you get zinc cations and hydrogen gas. You also saw that if you took one of the more reactive metals, like for example one of the alkali metals, and reacted it with a weaker acid such as water, again, you generated hydrogen gas. So for example, if you took potassium and reacted it with water, you got potassium hydroxide and hydrogen gas. And to balance that, we need 2 hydroxides, 2 waters, and 2 potassiums. You also saw that there are some metals, notably aluminum, that you can react with aqueous base and get hydrogen gas out. And so, for example, if we took aluminum metal and reacted it with hydroxide in the presence of water, then we wound up with everybody's favorite aluminum-containing anion and hydrogen gas. And to balance this one, you need 2 of these, and 2 of these, and 2 of these, and 6 waters to get 3 hydrogen gas. And so hydrogen, very little, capable of making a +1 cation, and also capable of making a -1 anion, makes Diatomic molecules that are very small, have a very strong bond, and are therefore quite easy to make